How far could we travel before the universe stops us? Space for sleep. Close your eyes for a moment. Not entirely. Keep just enough awareness to follow a single thought as it drifts outward, the way a breath of smoke rises from a candle and dissolves into a room. Imagine yourself standing outside on a clear night, far from any city, far from any road, in some field where the grass bends softly under a wind that carries no particular destination. Above you, the sky is not black. It only appears black because your eyes, those remarkable instruments shaped by 3 billion years of evolution in a world of limited light, cannot quite grasp what is truly there. What is truly there, in every direction you might choose to look, is an almost incomprehensible abundance. Stars beyond counting. Galaxies beyond imagining. Distances so vast that the human mind, trained as it is on the scale of forests and coastlines and mountain ranges, simply has no ready frame of reference. And yet, on this particular night, under this particular sky, allow yourself to ask one of the oldest questions our species has ever whispered to the darkness above. How far could we go if we tried? How far could we travel before the universe itself, with all its quiet and implacable laws, finally stopped us? It is a question that carries within it the entire weight of human longing. We have always looked outward. We have always leaned instinctively toward the horizon. Long before we understood what stars were, long before anyone knew they were distant suns, that they burned with nuclear fire, that they were separated by distances that make our entire solar system seem like a single grain of sand on an endless beach, our ancestors pointed at them and felt something that was not quite fear and not quite comfort, but something richer and stranger than either. Something like recognition. As though the cosmos, in its enormity, was a place we had once known and forgotten, and we were perpetually, gently trying to remember our way back. And now, armed with science, with mathematics, with telescopes that can detect the ancient light of galaxies that formed when the universe was barely a few 100 million years old, we are finally in a position to answer that question with something more than myth. The answer, it turns out, is both more wonderful and more humbling than anything our ancestors could have dreamed. Let us begin simply. Let us begin with speed. You are sitting still right now, or at least you feel that you are sitting still, but this is one of physics' most elegant illusions. You are in fact moving. You are rotating with the surface of the Earth at roughly 1,000 miles per hour. You are orbiting the Sun at approximately 67,000 miles per hour. You are being carried along with the entire solar system as it moves through the Milky Way galaxy at about 500,000 miles per hour. And the Milky Way itself is falling, along with the local group of galaxies to which it belongs, toward a massive concentration of matter called the Great Attractor, at speeds of several hundred kilometers per second. You are never still. The universe does not permit stillness. Everything is in motion, always, and has been since the very first fraction of the very first second after the Big Bang, when the cosmos erupted from a state of unimaginable density and heat and began its long, slow, magnificent expansion that continues to this moment and will continue long after every star in every galaxy has exhausted its fuel and gone dark. But when we speak of travel, when we speak of the human dream of sailing out among the stars, we mean something more intentional than this. We mean choosing a direction and accelerating toward it. We mean building a vessel, or perhaps something we do not yet have a word for, and pointing it at some distant light and asking, can we get there? The answer, for most of human history, was not even a question worth taking seriously. The stars were decorations. They were gods, or the homes of gods. They were points of navigation. They were beautiful, and they were remote, and their remoteness was simply a fact, like the hardness of stone or the coldness of deep water. It was not something to be overcome, it was something to be accepted. But we are a species that does not accept things easily. We are the animal that looks at a cliff and imagines a ladder. We are the creature that looks at the ocean and imagines a boat. And so, when we finally understood what stars truly were, when we grasped that they were suns, each one a furnace of thermonuclear reactions, each one potentially surrounded by its own family of worlds, the dream of reaching them became something we could no longer simply admire from a distance. We had to try. And in trying, we discovered the first, most fundamental limit the universe imposes on any traveler: the speed of light. Light moves through the vacuum of space at approximately 299,792 kilometers per second. This is not a fast train or a swift aircraft or even the fastest rocket humanity has ever launched. This is something of a different category entirely. In 1 second, a beam of light can travel 7.5 times around the circumference of the Earth. In 8 minutes and 20 seconds, it travels from the surface of the Sun to your eye. In about 4 years, it travels from our nearest stellar neighbor, the 3-star system of Alpha Centauri, to our own solar system. These numbers are extraordinary, and yet, as we will shortly discover, light speed is not nearly fast enough to traverse a universe that has spent nearly 14 billion years expanding in every direction simultaneously. The speed of light is both the fastest thing in the universe and, in the grandest of contexts, almost heartbreakingly slow. The reason light speed matters so profoundly is that it is not merely a speed limit in the way we commonly think of speed limits, some arbitrary threshold set by an authority that could, in principle, be revised. The speed of light is woven into the fabric of reality itself. It emerges from the deep structure of space and time. Albert Einstein understood this with a clarity that still leaves physicists slightly breathless when they think about it carefully. In his special theory of relativity, published in 1905, he showed that the laws of physics are the same for all observers moving at constant velocity, and that the speed of light in a vacuum is the same for all those observers regardless of their own motion. This seems, on first hearing, like a peculiar thing to say. We are accustomed to relative velocities. If you throw a ball from a moving train, the ball moves faster relative to the ground than it would if you had thrown it while standing still. But light does not work this way. Whether you are moving toward a light source or away from it, whether you are standing perfectly still or hurtling through space at 10,000 kilometers per second, you will measure the speed of light as exactly the same. This constancy has consequences so profound that they reshape not just physics, but our entire understanding of what space and time even are. The most famous of these consequences is time dilation. As an object moves faster, time passes more slowly for that object relative to a stationary observer. At low speeds, the speeds of everyday life, this effect is utterly negligible. But as a traveler approaches the speed of light, the effect becomes dramatic and then extreme. A spaceship traveling at 90% of the speed of light experiences time at roughly 44% the rate of a stationary observer. At 99% the speed of light, time aboard the ship moves at about 14% of the rate outside. At 99.9%, it moves at about 4.5%. The closer you approach the speed of light, the more time slows for you relative to the universe you are moving through, and this means that in principle, if you could somehow reach and sustain velocities very close to light speed, you could cross enormous distances within a single human lifetime, even though from the perspective of the universe around you, enormous amounts of time would be passing. This is one of the universe's more remarkable gifts, and it is entirely real. We have measured it precisely with atomic clocks on aircraft and in satellites. Time dilation is not a theory in the colloquial sense of the word. It is an experimentally confirmed feature of reality that we use in practical technology every day. Your GPS navigation system would fail to function correctly if the engineers who designed it had not accounted for relativistic time dilation. But time dilation, as magnificent as it is, does not solve the fundamental problem of cosmic travel. It solves the traveler's problem. It means that a crew aboard a relativistic spacecraft might experience a journey to a distant star as taking only a few years of their own subjective time. But it does nothing for the universe they left behind. The people who waved goodbye on Earth would age and die. Civilizations would rise and fall. The Sun, over sufficiently vast timescales, would exhaust its hydrogen fuel, swell into a red giant, swallow the inner planets, and eventually cool to a dim white dwarf. When the relativistic travelers finally returned, if they returned, they would return to a world that had aged thousands or millions or billions of years in their absence. Travel at near light speed does not cheat time. It only redistributes who experiences it. And there is another problem, one that becomes apparent the moment you begin to think seriously about what it would actually take to reach these velocities. Acceleration requires energy. The more mass a ship has, the more energy is required to accelerate it. And here is where the mathematics of relativity delivers its most sobering verdict. As an object's velocity approaches the speed of light, its effective mass, its resistance to further acceleration, increases without limit. A ship moving at 90% of light speed is significantly more massive than the same ship sitting still. A ship moving at 99% of light speed is vastly more massive. At the speed of light itself, the mass would be infinite, which means the energy required to reach that speed would also be infinite. And infinity is not a destination you can arrive at with a finite amount of fuel. The speed of light is therefore not merely a limit that is very difficult to exceed. It is a limit that is fundamentally, mathematically, physically impossible to exceed for any object that is mass. We call it the cosmic speed limit, and it is enforced not by any police force or regulatory agency, but by the deep structure of spacetime itself. Let us pause here for a moment. Let us breathe with this fact. Because it is easy to recite it, the speed of light cannot be exceeded by any massive object, and much harder to truly inhabit it. Think about what it means for a species that dreams of the stars. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. This means that even light, the fastest thing in the universe, takes 4 years and 3 months to make that crossing. A spacecraft traveling at 10% of the speed of light, which would require an almost unimaginable amount of energy with any technology we currently possess, would take over 40 years to reach it. A spacecraft traveling at 1% of the speed of light, already faster than anything humanity has ever built or is likely to build within the next century, would take 420 years. And Proxima Centauri is our neighbor. It is the closest possible destination beyond our solar system. The Milky Way galaxy is 100,000 light-years across. The Andromeda galaxy, our nearest large galactic neighbor, is 2.5 million light-years away. The observable universe extends roughly 46 billion light-years in every direction. These are not numbers. They are a kind of music, a music written in a register so deep that it is felt rather than heard. So perhaps the question changes. Perhaps instead of asking how fast we could travel, we ask something different. How far, in principle, could we reach, given unlimited time and unlimited patience? Imagine a civilization without the constraint of human lifespans. Imagine a species, or a set of machines built by a species, that could simply travel, generation after generation, century after century, not rushing, not burning extraordinary amounts of fuel to reach relativistic speeds, but simply moving steadily outward into the cosmos at a fraction of light speed, pausing at each star system to refuel and resupply and rest, then pressing on to the next. In principle, such a civilization could cross the Milky Way within a few million years. In the context of cosmic time, a few million years is not very long. Our galaxy is over 10 billion years old. A civilization that had existed for even 1% of the galaxy's age would have had more than enough time to visit every star system in the Milky Way, if it chose to do so. This is, in fact, one of the premises that underlies the famous Fermi paradox, the observation that given the age of the universe and the number of star systems within it, any civilization that developed interstellar travel even moderately early in the galaxy's history should have had ample time to spread throughout the entire galaxy before humanity even evolved. The fact that we see no evidence of such a civilization is a puzzle that has generated decades of scientific and philosophical debate, and which we shall circle back to in due time. But even this vision of patient, multi-generational, galaxy-spanning travel has its limits. And those limits are imposed not by physics in the way that the speed of light is imposed, but by the universe's own expansion, by the strange and wonderful and slightly terrifying fact that the cosmos is not static. It is not a fixed stage on which the drama of stars and planets unfolds. It is itself a participant in that drama. It is growing. It is stretching. And it is stretching in a way that is profound and ultimately inescapable consequences for any traveler who aims beyond a certain distance. To understand this, we need to go back almost 14 billion years to the event we call the Big Bang. It is a name that misleads more than it illuminates, because it suggests an explosion, a single point in space erupting outward into a pre-existing void. But this is not what happened. There was no pre-existing void. There was no surrounding space into which anything could explode. The Big Bang was not an explosion in space. It was an explosion of space itself. Every point in the universe was simultaneously the location of the Big Bang. The universe began as an extraordinarily hot, extraordinarily dense state in which all matter and energy were concentrated, and then, for reasons we do not fully understand, though theories abound, space itself began to expand. Not the contents of the universe expanding through space, but space itself stretching, growing, carrying the matter and energy within it along like raisins in a bread that is rising in the oven. And this expansion has never stopped. It continues to this day, and as we discovered to our considerable surprise in 1998, it is not slowing down. It is accelerating. The discovery that the universe's expansion is accelerating was one of the most shocking findings in the history of astronomy. Physicists had expected that the gravity of all the matter in the universe would gradually slow the expansion over time, the way a ball thrown into the air is slowed and eventually reversed by Earth's gravity. The expansion might slow to a halt and reverse into a big crunch, or it might slow asymptotically, and the universe would expand forever, but at an ever-decreasing rate. Either way, the expectation was deceleration. When two independent teams of astronomers, in 1998, announced that their observations of distant supernovae showed the opposite, that the expansion is in fact speeding up, the scientific community was, to put it mildly, unsettled. The discovery earned its authors the Nobel Prize in Physics, but it also inserted into our understanding of the cosmos a deep and unresolved mystery. What is driving the acceleration? We do not know. We call it dark energy, which is a name that means very little beyond our acknowledgement of our own ignorance. Dark energy appears to constitute roughly 68% of the total energy content of the universe. It is everywhere. It permeates all of space. And its effect is to push space apart, to accelerate the expansion, to drive galaxies and galaxy clusters beyond a certain distance ever faster away from us. And it is this accelerating expansion that imposes the universe's most profound and final limit on travel. Think of it this way. The universe has a horizon. Not a physical horizon like the edge of a flat Earth fantasy, not a wall or a barrier or a boundary you could approach and examine. It is a light travel horizon, an observational limit imposed by the fact that the universe is only about 13.8 billion years old, and light, even traveling at its maximum possible speed for the entire age of the universe, can only have reached us from a certain distance. Beyond that distance, there simply has not been enough time for any signal, any light, any information of any kind to reach us. We cannot see beyond it. We cannot know, in any direct observational sense, what is there. This is the edge of our observable universe, and it lies roughly 46 billion light-years away from us in every direction, farther than light could have traveled in the entire age of the universe, because the universe has been expanding while the light was traveling. The sphere of our observation is 46 billion light-years in radius, and it contains, by our best estimates, something like 2 trillion galaxies, each containing hundreds of billions to trillions of stars, each potentially surrounded by dozens of planets, at least some of which may harbor conditions suitable for life. 2 trillion galaxies. The number does not fit in the human mind. It must simply be accepted as a kind of poetry, a gesture toward immensity that language can point at but not contain. Now, within this observable universe, which galaxy or star system marks the farthest possible destination for a traveler setting out from Earth? This is where the physics becomes both fascinating and, depending on your temperament, either deeply melancholy or deeply beautiful. Because the answer is not simply 46 billion light-years. The answer depends crucially on the nature of dark energy and the rate at which the universe's expansion is accelerating. And what the mathematics tells us is genuinely remarkable. There is a sphere around our galaxy, a sphere with a radius of roughly 16 billion light-years, beyond which the expansion of space itself is so fast that even if we set a signal or launched a spacecraft at the speed of light today, it could never reach those destinations. The galaxies beyond this cosmic horizon are, in a very real and precise sense, permanently beyond our reach. Not because the distances are too large for any practical purposes, though they certainly are, but because the universe is expanding faster than light can cross those distances. Every moment, more galaxies slip beyond this event horizon, carried by the accelerating expansion into a realm of permanent inaccessibility. And in the very far future, in tens of billions of years, assuming humanity or its descendants still exist and still care to look, the sky will be almost entirely empty. The expansion will have carried every other galaxy beyond the observable horizon. The Milky Way will be alone in a dark and silent cosmos, its nearest neighbors receding faster than light, unreachable, unseen, as though the rest of the universe had never existed. It is a vision of the far future that is, in its particular way, one of the most haunting thoughts that physics has ever generated. But we are getting ahead of ourselves. Let us return to now. Let us return to the present, with its abundant cosmos, and its 2 trillion galaxies, and its questions about what is physically possible for a civilization that might, someday, have the will and the technology to try. Within our cosmological horizon, within the roughly 16 billion light-year sphere from which destinations are at least theoretically reachable, what are the actual obstacles? What stands between a traveler and the stars? The first obstacle is simply the void. Space is, almost unimaginably, empty. We speak of the space between stars as though it were a thin medium through which a traveler might wade, but it is nothing of the kind. The interstellar medium, The gas and dust that fills the space between stars and a galaxy like the Milky Way is the most perfect vacuum in nature, emptier than anything we can create in a laboratory on Earth. There are roughly a handful of hydrogen atoms per cubic centimeter in the average interstellar medium, compared to the approximately 27 million trillion molecules in every cubic centimeter of air you are breathing right now. The distances between stars are measured in light years, and a light year is approximately 9.5 trillion kilometers. This is not a distance that scales naturally onto human experience. There is no analogy that fully captures it, though many have been tried. If the sun were the size of a grapefruit and you placed it on a table, then on the same scale, the nearest star would be another grapefruit sitting in Tokyo or New York, depending on where you set the first one. Between them, almost nothing. Almost perfect emptiness. This is what a starship must cross. And it must cross it with a crew that requires food and water and air and warmth, that is susceptible to radiation and isolation and the slow psychological erosion of confinement that ages and dies, and must be replaced by new generations if the journey takes longer than a single human lifetime. The engineering challenges alone are enough to give pause to the most optimistic space enthusiast. Then there is the question of fuel. To accelerate a spacecraft to even a few percent of the speed of light requires an extraordinary amount of energy. The Voyager probes, our farthest traveled human artifacts, are currently about 23 billion kilometers from Earth and took over 45 years to get there. They are moving at roughly 17 kilometers per second, which is about 0.006% of the speed of light. At this speed, a journey to Proxima Centauri would take roughly 73,000 years. Humanity has not existed as a species for that long. Our entire recorded history spans only a few thousand years. The agricultural revolution, which gave rise to the first cities and the first civilizations, began roughly 12,000 years ago. To contemplate a journey of 73,000 years is to contemplate something outside the frame of everything we have ever known. And Voyager is not even a vehicle designed for interstellar travel. It is simply moving in that general direction because of the gravitational slingshots that carried it past Jupiter and Saturn. An actual interstellar mission would need far more speed than this, and achieving far more speed requires far more energy, and storing the energy in a form that can be carried aboard a spacecraft without the mass of the fuel itself defeating the purpose of the journey is one of the central unsolved problems of deep space travel. Physicists and engineers have proposed many creative solutions over the years, and it is worth spending some time with them, because they illuminate both the ingenuity of human thought and the implacability of physical law. One of the most elegant proposals is the Bussard ramjet, conceived in 1960 by physicist Robert Bussard. The interstellar medium, sparse as it is, does contain hydrogen, and hydrogen is fuel for nuclear fusion. If a spacecraft could scoop up interstellar hydrogen as it flew, using a vast electromagnetic funnel to gather the sparse atoms ahead of it and follow them into a fusion reactor, it could, in principle, accelerate indefinitely without carrying any fuel of its own. The idea is beautiful in its simplicity. The cosmos itself becomes the filling station, and a sufficiently advanced spacecraft could, theoretically, reach relativistic speeds and cross the galaxy within a human lifetime. The problem is that the interstellar medium is not nearly dense enough to supply a practical ramjet at the speeds we can currently imagine building for, and the drag created by the magnetic funnel itself might outweigh the thrust produced by the fusion reaction. Later analyses have shown that the Bussard ramjet, in its original form, is almost certainly impractical. But the idea sparked an entire tradition of creative thinking about how to extract energy from the environment of deep space, and that tradition continues today. Another proposal is the solar sail, or, for interstellar travel, the laser sail. A large, thin mirror in space, pushed by the pressure of light itself, can be accelerated without carrying any fuel at all. The photons that strike the mirror and reflect from it transfer a tiny but continuous momentum, and in the absence of friction, even a tiny continuous force is enough to accelerate an object to significant speeds over time. A laser sail driven not by sunlight, but by a powerful directed laser array on Earth, or on the Moon, or in Earth orbit, could, in principle, accelerate a small probe to a significant fraction of the speed of light within the inner solar system, then coast to a nearby star. This is the central concept behind Breakthrough Starshot, a research initiative announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner, which proposes sending a fleet of ground-scale wafers equipped with cameras, sensors, and communication equipment to Alpha Centauri on laser sails, aiming to reach 20% of the speed of light and arrive within about 20 years of launch. The challenges are formidable. The laser array required would be of unprecedented power. The sail materials must be extraordinarily thin and reflective, and a grand-scale probe has limited capabilities for scientific observation and absolutely no capacity for human passengers. But the proposal is not physically absurd. It lies within the theoretical limits of what physics permits, even if it lies well beyond our current engineering capabilities. For human travel, rather than robotic probes, the energy requirements are far more severe. A crewed interstellar spacecraft must carry not only its passengers and their life support systems, but the fuel to decelerate at the destination. Otherwise, the ship arrives going so fast that it passes through the target star system in a matter of hours and continues into the void beyond. Deceleration requires as much energy as acceleration, which means the total energy budget roughly doubles, and when you account for the mass of the deceleration fuel, and the fuel needed to carry the fuel, the numbers become formidable very quickly. The most efficient chemical rockets ever built, the Saturn V that carried astronauts to the Moon, are many orders of magnitude too inefficient for interstellar travel. Even nuclear thermal rockets, which are far more energetic, fall well short of what is needed. Nuclear pulse propulsion, using a series of nuclear bombs detonated behind a spacecraft to push it forward, could, in principle, achieve a few percent of light speed, and was actually studied quite seriously in the 1950s and 1960s under the name Project Orion. But a few percent of light speed, while far beyond anything we have achieved, still implies a journey of centuries to the nearest star. The truly relativistic velocities that would compress those centuries into a human lifetime require matter-antimatter annihilation, which is the most energetically efficient possible reaction and releases energy equivalent to the full mass of both the matter and antimatter consumed. The problem is that we currently produce antimatter only in particle accelerators, a few nanograms at a time, at enormous expense, and storing antimatter is extraordinarily difficult since it annihilates on contact with any ordinary matter. A matter-antimatter rocket capable of carrying humans to the stars would require kilograms or tons of antimatter, and the gap between what we can produce and what we would need is, at present, essentially unbridgeable. But let us not be too quick to declare defeat. Let us remember where we have come from. 350 years ago, the fastest mode of transportation available to any human being on Earth was a horse. 120 years ago, the first powered heavier-than-air aircraft flew for 12 seconds and covered 37 meters. 60 years ago, the first human being left Earth's atmosphere. 50 years ago, human footprints were pressed into the dust of another world. The pace of technological advancement in the modern era defies any attempt to extrapolate it conservatively. And the laws of physics do not forbid interstellar travel. They make it difficult. They make it enormously demanding of energy and time. They impose limits on speed and, as we will explore, on the range of destinations that can ever be reached. But within those limits, the universe does not say no. The universe says, if you can find the energy, you can go there. And for a technological civilization that has been advancing for only a few thousand years out of a possible lifespan of billions, the phrase, if you can find the energy, is not necessarily a barrier. It may be a challenge. And challenges, as we are a species that has demonstrated repeatedly, are among the things we do best. Let us now think about something that physics does explicitly forbid, or at least appears to, and let us think about it carefully, because the line between prohibition and extreme difficulty is not always obvious. The idea of faster-than-light travel has been a staple of science fiction for as long as science fiction has existed. Warp drives, hyperspace, jump gates, wormholes, these narrative devices allow characters and stories to cross the galaxy in days, or hours, or seconds, bypassing the frustrating constraint of light speed and making the cosmos dramatically navigable. In the context of storytelling, they are enormously useful. In the context of physics, they are considerably more complicated. General relativity, Einstein's theory of gravity, published in 1915, which describes gravity not as a force, but as the curvature of spacetime caused by mass and energy, does not explicitly forbid faster-than-light travel. What it forbids is faster-than-light travel through spacetime, the kind of travel where you are moving relative to the surrounding space faster than light does. But what it does allow, at least mathematically, is the possibility of distorting or manipulating spacetime itself in ways that could effectively allow distant points to be traversed in less time than light would take. The most famous of these possibilities is the wormhole. A wormhole, in the mathematical sense, is a topological feature of spacetime, a shortcut, or tunnel, connecting two distant points. Einstein and physicist Nathan Rosen first described such structures in 1935, which is why they are sometimes called Einstein-Rosen bridges. In the simplest conception, imagine the universe as a flat piece of paper. 2 points on this paper might be a meter apart as measured along the paper's surface. But if you fold the paper so that those 2 points approach each other, you could poke a hole through both layers and create a shortcut between them that is much shorter than the path along the paper's surface. A wormhole is the three-dimensional, actually four-dimensional, in space-time, analog of this shortcut. If one could travel through a wormhole, one could effectively move from one point in the universe to a distant point without traversing the vast space between them. From the perspective of someone watching from outside, it would appear as though the traveler had moved faster than light, though technically the traveler would have moved through space-time, not through space, and the distinction is not merely semantic. The problem with wormholes is that they are extraordinarily unlikely to exist naturally, and if they did, they would almost certainly be unstable. A natural Schwarzschild wormhole, of the kind that appears in the mathematics of general relativity, would collapse so quickly that nothing could pass through it. It would pinch shut in far less than the time it would take for a signal moving at light speed to cross it. To keep a wormhole open long enough for a traveler to pass through, it would require something called exotic matter, material with negative energy density, a property that is deeply at odds with our experience of ordinary matter. Quantum mechanics does suggest the existence of certain phenomena, the Casimir effect, for instance, where the vacuum fluctuations of quantum fields between two closely spaced conducting plates create a measurable negative energy density that demonstrate negative energy is not entirely impossible. But the amount of negative energy required to stabilize a traversable wormhole would be extraordinary, likely equivalent to the total positive energy content of a large star or galaxy, concentrated in a very small region. Whether this is physically achievable, even in principle, is genuinely unknown. It sits in the tantalizing territory between our knowledge and our ignorance, where many of the most interesting questions in physics live. Another proposal that has generated considerable excitement and considerable controversy in the physics community is the Alcubierre warp drive, proposed by Mexican physicist Miguel Alcubierre in 1994. Alcubierre's idea was to describe a spacetime geometry in which a region of space could be manipulated such that space itself contracted in front of a spacecraft and expanded behind it, carrying the ship along with it like a surfer riding a wave. The clever feature of this proposal is that the ship itself would not be moving through space in the usual sense. It would be sitting still in a bubble of flat spacetime, while the bubble moved. And because the limit imposed by special relativity applies to objects moving through space rather than to space itself, this technically circumvents the cosmic speed limit. Alcubierre showed that such a geometry is consistent with the equations of general relativity, but he also showed that, like wormholes, it requires exotic matter with negative energy density and likely an enormous amount of it. Later analyses, including work published within the past several years, have proposed modifications of the original Alcubierre geometry that would reduce the exotic matter requirement, but the requirement has not been eliminated, and the fundamental question of whether the necessary exotic matter can be produced and controlled remains deeply uncertain. The warp drive exists, for now, as a mathematical possibility rather than an engineering prospect. But it exists, which is more than it did before Alcubierre wrote his paper, and in physics, mathematical existence is not nothing. It is the first step. Now let us take a deep breath and widen our gaze. Let us step back from the engineering questions, the fuel, the propulsion, the exotic matter, the long centuries of travel time, and think about what the universe looks like from the perspective of a truly vast timescale. Because one of the most profound limits on cosmic travel is not a limit that announces itself immediately. It is a limit that creeps up slowly over billions of years and becomes absolute only in the far future. It is the limit imposed by the accelerating expansion of the universe, by dark energy, by the fact that the cosmos is not merely large but is actively, perpetually growing larger, and at an accelerating rate. We have already established that there exists a cosmological event horizon, a sphere roughly 16 billion light-years from the Milky Way beyond which even signals in today, traveling at light speed, can never reach their targets because the space between here and there is expanding too fast. But this horizon is not fixed. As the universe continues to expand and the expansion continues to accelerate, this horizon actually shrinks, not in absolute terms, but in terms of the fraction of the universe's total content that lies within it. More and more galaxies, as the universe ages, recede beyond the point of contact. The observable universe grows larger, as the light from ever more distant objects finally has time to reach us, but the reachable universe, the subset of the observable universe with which we could ever hope to physically interact, even with perfect technology and unlimited energy, grows smaller. The universe is, in this very specific sense, becoming lonelier with time. What does this mean for a civilization with vast technological resources and an unlimited horizon of time? It means that the window for exploration and contact with the broader cosmos is not infinite. It opens gradually as technology develops and then begins, slowly and then inexorably, to close as the expanding universe carries more and more destinations beyond all possible reach. A civilization that waits too long to explore, that spends its first billion years developing peacefully inward before turning its attention outward, may find that the number of reachable galaxies has shrunk substantially from what it was when it first arose. The universe rewards urgency. The universe is, in the longest possible view, a shrinking opportunity. This is not an intuitive thought. Our instinct, surveying the cosmos with its trillions of galaxies, is to feel that there is more than enough out there for any civilization to explore, however long they wait. And at present, this is indeed true. The observable universe contains roughly 2 trillion galaxies, and the reachable subset of those, the ones a sufficiently motivated civilization could reach before they recede beyond the cosmic horizon, has been estimated at several 100 billion to 1 trillion galaxies. The Milky Way, with its 200 to 400 billion stars, is merely one among this incomprehensible abundance. But the abundance is temporary. In about 100 billion years, a period about 7 times the current age of the universe, but still a finite and calculable time, all galaxies outside the local group will have receded beyond the event horizon and will be permanently unreachable. Only the galaxies gravitationally bound to ours will remain accessible. The Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, the Magellanic Clouds, and the few dozen smaller galaxies that make up the local group will eventually merge into a single large elliptical galaxy, surrounded by the absolute darkness of an expanding void, the rest of the cosmos invisible and inaccessible, the other 2 trillion galaxies as thoroughly beyond reach as if they had never existed. But even within the local group, even within this final cosmic redoubt, the story is not over. The merged galaxy will persist for billions of years more. Its stars will age and die and not be replaced, because the gas available for new star formation will gradually be consumed. The universe, on this timescale, is not a place of permanent abundance. It is a place of temporary magnificence, a fireworks display of stellar creation and stellar death that will run its course over trillions of years, leaving behind at last a dark and cold and silent cosmos of black holes and dim stellar remnants, white dwarfs cooling toward black dwarfs, neutron stars spinning down to rest, the last sparks of nuclear fire going out one by one across a universe grown almost incomprehensibly sparse and cold. This ultimate fate of the universe, which physicists call the heat death, or the big freeze, is not a cheerful vision. It is the long-term prediction of thermodynamics applied to an expanding universe, and it follows from the second law of thermodynamics, which states that the total entropy of a closed system always increases over time. Entropy is, loosely, a measure of disorder, or more precisely, a measure of the number of different ways the components of a system can be arranged while producing the same macroscopic properties. A universe rich in temperature differences and density contrasts. A young, hot, structured universe full of stars and galaxies, and the complex chemistry they enable, is a universe of relatively low entropy, its energy concentrated in useful forms. As time passes, and the universe expands and cools, entropy increases. Energy becomes more uniformly distributed. Temperature differences flatten out. The energy that once drove stars and powered the chemistry of light diffuses into a nearly uniform, nearly empty, nearly cold background. Eventually, after a time span so vast it almost defies expression, on the order of 10 to the power of 100 years or more, even the black holes that persist after all the stars have died will have evaporated through Hawking radiation, leaving the universe utterly uniform and cold and dark, with no significant energy differences anywhere, no gradients to drive any process, no chemistry possible, no complexity of any kind. This is the true end, not with a bang but with an absolute and final silence. And yet, even this bleak vista has a certain majesty to it. There is something almost meditative about contemplating the full arc of the cosmos, from its incandescent beginning to its long and brilliant middle age of stars and galaxies and, perhaps, the emergence of consciousness in 100 billion places, to its long and patient fading into the cold of maximum entropy. The universe does not exist for us. It did not arise to please us or to accommodate our dreams of exploration. It follows its own laws with perfect indifference, and those laws, as we have seen, impose real and fundamental limits on how far any traveler can go. But within those limits, there is so much. There is almost enough to occupy a civilization for the entire age of the universe, if it begins early enough and moves with purpose and curiosity. The limits are not a prison. They are a frame, and within a frame, art is possible. Let us return now to the question of biology, to what it means specifically for creatures like us to contemplate these distances. Human beings evolved on a single world orbiting a single star. Our bodies are perfectly suited to that world. Its gravity, its atmosphere, its temperature range, its radiation environment, its 24-hour rotation, its seasonal cycles. We are an intensely local phenomenon. We are, in the deepest sense, creatures of a particular place. And when we contemplate leaving that place, not just traveling to the moon or to Mars, which are within the gravitational sphere of influence of our own sun, but genuinely departing for the stars, we must confront the fact that our biology was not designed for such a journey. It was designed, by the blind process of natural selection, to maximize reproductive success on a single blue world under a particular yellow sun. The cosmos, vast and magnificent as it is not our natural habitat. The radiation environment of deep space is perhaps the most immediate biological challenge. Earth's magnetic field and atmosphere shield us from a constant barrage of high-energy particles, cosmic rays from distant supernovae and other energetic astrophysical events, solar wind, ultraviolet radiation. In deep space, beyond the protection of any planet's magnetic field, these particles would penetrate a spacecraft and damage the DNA of any crew aboard, increasing cancer risk and potentially causing other serious health effects over the course of a long voyage. The longer the journey, the more cumulative radiation damage accumulates. For a voyage of decades or centuries, shielding becomes a critical engineering challenge, and the most effective shielding, thick layers of dense material, adds mass to the spacecraft, requiring more fuel to accelerate, compounding the energy problem we have already discussed. Then there is the question of microgravity. The human body, evolved in Earth's gravitational field, begins to deteriorate in the absence of gravity with startling speed. Muscles atrophy, bones lose density, the cardiovascular system weakens, the vestibular system becomes confused. These effects are well documented from observations of astronauts aboard the International Space Station, and while exercise regimens can partially mitigate them, they cannot be eliminated entirely. On a voyage of years or decades in microgravity, the physical deterioration of the crew would be severe. Solutions have been proposed, rotating sections of the spacecraft to create centrifugal force that mimics gravity, for instance, but implementing them adds complexity and mass and engineering challenges of its own. The human body requires gravity. It evolved in gravity. Depriving it of gravity is, in the long run, simply bad for it. And then there is the mind. We are social creatures. We evolved in bands of a few dozen to a few hundred individuals, surrounded by a natural environment rich with variety and change and sensory input. The psychological challenges of long-duration space travel, the isolation, the confinement, the monotony, the constant low-level stress of living in a dangerous artificial environment, the loss of connection to everything familiar, are profound and not fully understood. We have some data from long-duration missions on the International Space Station, from Antarctic winter-over crews, from submarine crews, from studies of individuals in isolation. The data are not entirely reassuring. Conflict, depression, sleep disruption, and cognitive decline are all documented responses to the conditions of extreme confinement and isolation. For a voyage lasting not months, but years or decades or centuries, these challenges would need to be addressed with a seriousness and sophistication that goes far beyond anything we have yet developed. Some have proposed solving the biological problem not by making humans tougher or more adaptable, but by changing what is being said. Rather than biological humans, fragile, radiation-sensitive, gravity-dependent, short-lived, psychologically complex, perhaps the first true interstellar travelers will not be human at all in the conventional sense. They might be digital minds, patterns of information that encode personality, memory, knowledge, creativity, everything that makes a person who they are, running on computational hardware that is radiation-hardened, modular, easily repaired, and capable of simply pausing, turning itself off, for the centuries of transit time and awakening on arrival at the destination, perceiving the journey as no more than a moment of dreamless sleep. This is the concept of mind uploading, of digital consciousness, and it rests on the assumption that consciousness is substrate independent, that what matters is the pattern, not the specific physical material in which the pattern runs. This is a philosophical position, as much as a scientific one, and it is deeply contested. But if it is correct, and the question of whether it is correct may be the most consequential question humanity will ever investigate, then the obstacles to interstellar travel are dramatically reduced. A digital mind requires no food, no water, no radiation shielding for biological tissue, no gravity, no social stimulation in the conventional sense. It requires only power and computational substrate, and in a spacecraft optimized for digital rather than biological passengers. Both are manageable engineering challenges. Alternatively, one could imagine sending something even simpler, not a digital mind but a self-replicating robotic system capable of arriving at a destination, using local resources to build what it needs, and then transmitting information back. This is the concept that engineers call a von Neumann probe, named after the mathematician John von Neumann, who first analyzed the theoretical properties of self-replicating machines. A civilization sufficiently advanced to build a von Neumann probe could seed the galaxy with them, each one arriving at a new star system, using local materials to build copies of itself, and sending those copies onward to the next system, while also transmitting observations of its current destination back to the origin civilization. A fleet of such probes, launched from a single world, could in principle survey the entire Milky Way within a few million years, much faster than any biological civilization could physically travel. And the fact that we see no evidence of such probes in our solar system, no alien machines quietly cataloging our world, no signals that might be the transmissions of a probe reporting back to its creators, is yet another facet of the Fermi paradox, and another reason to wonder about the distribution of intelligence in the cosmos. There is a loneliness in this wondering that is worth sitting with for a moment, because if we are, in fact, the only civilization that has ever arisen in this galaxy, if no other species has ever achieved the technological sophistication to launch even robotic probes, let alone crewed spacecraft, in all the billions of years that the Milky Way has been producing stars and planets, then the cosmos is, for all practical purposes, ours alone. Not in any possessive sense, but in this sense of availability, of unclaimed opportunity. Every star system, every planet, every moon, every asteroid belt in 100 billion star systems would be unexplored, unseen by any curious eye, waiting in the darkness for the first time that anything capable of comprehension arrived to observe it. The responsibility of that inheritance is difficult to articulate. It feels, on a visceral level, like something that matters. It feels like a calling. But there is another possibility. Perhaps many civilizations have arisen, and they have not expanded, have not sent probes, have not reached out. Perhaps the universe is not merely empty but deliberately quiet. The reasons a civilization might choose silence and isolation over expansion are many, and not all of them grim. Perhaps expansion simply becomes less interesting as civilizations mature. Perhaps the inner worlds of digital consciousness, the vastness of simulated realities, the depth of art and philosophy and science that can be explored without leaving home, perhaps these prove so rich and so endlessly generative that the stars simply lose their appeal. Perhaps the energy costs of expansion, once fully calculated, seem not worth paying. Perhaps civilization solve the problems of mortality and meaning in ways that make the conquest of physical space unnecessary. The cosmos may be full of civilizations that have each, in their own way, looked at the void between the stars and decided, thoughtfully and deliberately, to stay home. Not from fear or limitation, but from a kind of profound sufficiency, a recognition that one world, fully understood, fully cherished, fully explored in all its depth and complexity, is enough. These speculations lead us back to the original question, the one we began with, from a direction we might not have expected. How far could we travel before the universe stops us? The physical answer is, as we have seen, that the universe imposes several nested limits. The first is the speed of light, which prevents any massive object from exceeding it, and makes even short interstellar distances enormously challenging. The second is the energy requirement for propulsion, which renders the speeds needed for practical interstellar travel far beyond our current technology, though not beyond the reach of physics. The third and most absolute is the cosmological event horizon, the sphere beyond which the accelerated expansion of the universe prevents even light from ever arriving, a sphere that is slowly shrinking as the expansion accelerates, and that will eventually encompass only the local group of galaxies. But there is also a philosophical answer to the question, and the philosophical answer is both simpler and stranger than the physical one. The universe may stop us before we reach the nearest star, or it may not stop us until we have colonized the local group. The actual limit depends not just on physics, but on choices, on what we decide to do, on how much of our civilization's energy and creativity and determination we choose to invest in the project of reaching outward. The universe imposes constraints. It does not determine outcomes. The outcomes depend on us, or on whatever forms of intelligence may someday carry forward the project of understanding that we have, in our brief and remarkable existence, begun. Consider what we have already done in the short time we have been capable of asking these questions. The age of modern science is, at most, 400 years old. The age of spaceflight is less than 70 years old. And in those 70 years, we have sent probes to every planet in our solar system and to several of their moons. We have landed on the moon and on Mars. We have soft landed on comets and on asteroids. We have sent spacecraft beyond the heliopause, the bubble where the solar wind gives way to the true interstellar medium, and those spacecraft are still transmitting. We have detected gravitational waves from the mergers of black holes and neutron stars billions of light years away. We have directly imaged black holes. We have discovered thousands of exoplanets, including dozens in the habitable zones of their stars, and we have begun to analyze their atmospheres for signs of life. All of this in the first 70 years of the space age, by a civilization that had no concept of powered flight 125 years ago. The pace of discovery is not slowing. If anything, it is accelerating. The James Webb Space Telescope is currently showing us galaxies that formed when the universe was only a few 100 million years old, revealing the cosmic dawn with a clarity that was inconceivable even 20 years ago. Powerful new ground-based and space-based observatories are coming online that will survey hundreds of millions of stars for signs of planetary companions and biosignatures. The engineering challenges of interstellar travel are beginning to be studied seriously for the first time, not as science fiction, but as long-range playing problems for a spacefaring civilization. And the fundamental physics of propulsion, the possibilities of matter-antimatter engines, of laser sails, of whatever exotic physics might eventually be harnessed if quantum gravity and a theory of everything yield insights we cannot yet anticipate, remains a field of active and increasingly sophisticated inquiry. We do not know if we will ever reach the stars. We do not know if any human being or any entity descended from humanity will ever stand on the surface of a planet orbiting another sun and look up at a strange sky and hear a wind that has never before carried the sound of anything that could wonder at it. We do not know this. And the not knowing is not a deficiency. The not knowing is where all the most interesting things live. What we can say, with confidence grounded in physics and history both, is that the universe does not stop us arbitrarily. It does not stop us because it dislikes us, or because it has any preference in the matter at all. It stops us, to the extent that it stops us, through the operation of laws that are the same everywhere, for everyone and everything. The speed of light applies to alien civilizations in distant galaxies, just as surely as it applies to us. The second law of thermodynamics will claim their stars as surely as it will claim ours. The cosmological event horizon will eventually isolate them in their local group of galaxies, just as it will eventually isolate us. The universe is, in this sense, magnificently fair. It gives everyone the same rules. What you do with those rules is your own affair. And there is something else. Something that is easy to miss when we focus on the barriers, on the distances, the energies, the times, the limits. Something that might be the most important thing of all. We are here. We are asking these questions. We are a collection of atoms forged in the hearts of dying stars, assembled by 4 billion years of biological evolution on a small rocky world orbiting an unremarkable star in an outer spiral arm of one galaxy among 2 trillion, and we have somehow arranged ourselves into a form that can look up at the sky and wonder. We have built instruments that extend our senses across billions of light years. We have developed mathematics that describes the curvature of spacetime and the behavior of quantum fields to energies we will never be able to create in a laboratory. We have told each other stories about the stars for as long as we have been capable of language, and those stories have gradually, tentatively, transformed into something that looks a great deal like understanding. This is not a small thing. This is, as far as we know, an extraordinarily rare and precious thing. The universe is under no obligation to produce creatures capable of understanding it, and yet here we are. Whether this is an accident of probability or something more significant, whether consciousness and understanding are, in some sense, built into the structure of a universe that is as it is and not otherwise, is a question that sits at the boundary between science and philosophy, and we will not resolve it here. But the fact of it deserves to be noticed, deserves to be held for a moment, the way you might hold a perfect stone found on a beach, feeling its weight and its smoothness, recognizing that it is exactly what it is and nothing else. The night is still clear above that imaginary field where we began. The grass is still bending in its gentle wind. And overhead, the stars are exactly where they have always been, not where they seem to be, which is where they were decades or centuries or thousands of years ago, when the light we are seeing now left them, but where they truly are, at this moment, which we can calculate but never directly see. They are burning. They are dying. Some of them have already died. Others will burn for 100 billion years more. And around some of them, perhaps, though we do not yet know, there are worlds where other creatures look up at a sky that contains our sun as a single faint point of light, and wonder, as we wonder, whether they are alone. The universe stops us, ultimately, at its event horizon, at the boundary where the expansion of space becomes faster than light, where no signal can ever cross, where the rest of the cosmos will one day vanish from all possible perception. Beyond that boundary, we are, by any physical definition, alone. But the boundary is not close. It is 16 billion light years away. Within that boundary lie hundreds of billions of galaxies, trillions upon trillions of stars, and a period of accessible cosmic history measured in tens of billions of years. This is our inheritance, not the entire universe, but more of it than we can possibly imagine exploring in the time available to us. And the time available to us, though finite, is vast. We have time to dream, and then to try, and then to dream again. There is one more thought to carry with you, as we let this contemplation settle into the silence of its natural conclusion. We tend to think of limits as losses. A speed limit is a restriction. An event horizon is a wall. The heat death of the universe is a tragedy. And there is some justice in these feelings. The universe's limits do constrain us, do prevent us from doing things we might wish to do ultimately foreclose possibilities that feel precious. But limits are also the frame within which everything meaningful happens. Music is only music because notes have definite pitches and definite durations. A painting is only a painting because it exists within a frame, because the canvas has edges. A story is only a story because it has a beginning and, eventually, an end. The universe, with its finite age, and its cosmic speed limit, and its expanding horizon, and its ultimately entropic fate, is a story with edges. And within those edges, within this extraordinary bounded space of possibility, everything we have ever loved and known and wondered about has happened. Every civilization that has ever risen, every star that has ever burned, every atom that has ever been assembled into something capable of looking up and asking, how far could we go? Far enough. If we have the courage to try far enough. The grass bends. The stars burn. The universe expands into its own mystery, and we watch it go, and we follow as best we can, and the following is everything. There is a peculiar intimacy in the dark. Not the dark of a room with curtains drawn, not the dark behind closed eyes, but the true dark of an open sky on a moonless night, far from any human settlement, where the absence of artificial light allows the cosmos to reveal itself with its full and ancient splendor. In that kind of dark, the Milky Way is not a faint smudge but a river of light so wide and so complex that looking at it feels less like looking at a sky and more like looking through a window into something you are not prepared to see. The band of our own galaxy, viewed from inside it, stretches from horizon to horizon in a luminous arc of hundreds of billions of stars, their individual lights blurred together by distance into a continuous glow, punctuated by the dark threads of dust clouds where new stars are forming and where, perhaps, new worlds are assembling themselves from the raw materials of exploded ancient suns. To stand beneath that sight is to feel two contradictory things simultaneously: a profound smallness, a recognition of one's own near total insignificance in the scale of what is overhead, and a profound exhilaration, a sense of being part of something so large and so old, and so astonishing that the very fact of perceiving it seems almost impossibly fortunate. This experience, standing in genuine darkness beneath the full weight of the unobstructed sky, is increasingly rare. The majority of the human population now lives in areas where light pollution has erased the Milky Way from visibility. Generations of children are growing up under skies that show them a few dozen of the brightest stars and nothing more, disconnected from a sight that shaped human imagination for the entire duration of our species' existence before the advent of electric light. There is a loss in this that we are only beginning to understand and articulate, a severing from the context in which so many of our deepest questions first arose. But the loss is remediable. A drive into the countryside, a clear night, a place where the horizon is open, and the sky is still there, unchanged by our inattention, waiting with the same patient and ancient light that greeted every generation before ours. Let us think about that light for a while. The light that reaches your eye from the farthest stars you can see with the naked eye left those stars roughly 1,000 to a few thousand years ago. This means that what you see when you look at the sky is not a snapshot of the present but a temporal collage, each point of light representing a different moment in the past, some separated by centuries, some by millennia, a few by millions of years, for the faintest naked eye objects at the limits of perception. The Andromeda galaxy, that faint smudge visible on a dark night, the farthest object human eyes can detect unaided, shows you light that left it approximately 2.5 million years ago, when our own ancestors were small-brained bipeds scavenging the savanna of eastern Africa, not yet making fire, not yet carving stone into tools that could last the ages. The universe you see is the universe of many pasts layered upon each other, a history written in photons traveling at the only speed the universe allows for information. And when you extend this thought to what our telescopes can see, to the billions of galaxies that become visible when you point a sufficiently powerful instrument at any patch of dark sky and wait long enough, the temporal depth becomes staggering. The Hubble Ultra Deep Field, a famous image created by pointing the Hubble Space Telescope at an apparently empty region of sky and gathering light for over 11 days, revealed approximately 10,000 galaxies in a region of sky smaller than a grain of sand held at arm's length. Many of those galaxies are seen as they were over 13 billion years ago, as they were when the universe was only a few 100 million years old, when the first stars were just beginning to ignite and the universe was still adjusting to its own newness. These are not galaxies as they currently exist. They are fossils of the young universe, time capsule images preserved in the long journey of their ancient light. The galaxies themselves have long since evolved, merged with neighbors, changed their shapes and compositions and rates of star formation. Some of their stars have lived and died and been replaced many times over in the billions of years the light was traveling. What we see in those images is a ghost, beautiful and precise, of something that no longer exists in the form we are seeing it. This layered temporality of astronomical observation is one of the things that makes the night sky so philosophically rich. We do not observe the universe as it is. We observe it as it was, at different distances corresponding to different times, and from that fragmentary and time-lagged evidence, we must reconstruct our model of what the cosmos currently looks like and what it will look like in the future. This is the fundamental challenge and the fundamental beauty of cosmology. It is a science of reconstruction from incomplete and temporally displaced evidence, like archaeology, but on the grandest possible scale. And like all great detective work, it requires not just data but imagination, the ability to look at the evidence and see, behind it, the processes and structures that produced it. One of the most profound reconstructions that modern cosmology has achieved is the reconstruction of the universe's infancy, the first few 100,000 years after the Big Bang, before any stars or galaxies existed, when the cosmos was a hot, dense, nearly uniform plasma of particles and radiation. The evidence for this reconstruction is the cosmic microwave background radiation, a faint glow of microwaves that fills the entire sky uniformly, the afterglow of the Big Bang itself, the light emitted when the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms for the first time, allowing the previously opaque plasma to become transparent and the radiation to stream freely outward. That light has been traveling for 13.8 billion years. It comes from every direction in the sky because it was emitted from the surface of a sphere that surrounded our position in all directions when the universe was only about 380,000 years old. When we detected with microwave telescopes, as the COBE, WMAP, and Planck spacecraft have done with increasing precision over the past 3 decades, we are seeing the universe as it was before any of the structures we recognize today had formed. The cosmic microwave background is the oldest observable thing in the universe, a window onto the primordial state of the cosmos, and it carries within its tiny temperature fluctuations, variations in temperature of only a few parts in 100,000 across different directions in the sky, the seeds of everything that came after, the slight overdensities that gravity would amplify over billions of years into the galaxies and galaxy clusters and cosmic web of filaments and voids that characterize the large-scale structure of the universe today. To look at an image of the cosmic microwave background, to see that ancient light rendered as a map of subtle temperature variations, the fossil of the first light that could ever travel freely through the cosmos, is to look at the universe's earliest infancy. It is an act that ought to produce something close to reverence, or at least the secular equivalent of reverence, a deep and sustained attention in the presence of something that is both vastly older than us and intimately connected to everything about us. The atoms in your body were forged in stellar furnaces that were powered by nuclear reactions whose parameters were set in the first few minutes after the Big Bang. The carbon, the oxygen, the iron, the calcium, every element heavier than helium was built by stars that formed from the primordial hydrogen and helium produced in those first minutes, then dispersed by stellar winds and supernova explosions back into the interstellar medium to be incorporated into new stars, new planets, new molecules, and eventually into the long and winding chemistry that produced life. You are, in a very literal sense, a child of the Big Bang. The universe's history is your personal history at the deepest level of the physical, and every observation we make of the cosmos is in some sense a form of self-knowledge. This is what Carl Sagan meant when he said, "We are made of star stuff." It was not a metaphor. It was a statement of chemistry and astrophysics. The hydrogen in your body is as old as the universe itself. It was produced in the Big Bang, has been incorporated into various structures over the intervening 13.8 billion years, and found its way at last into the water molecules that make up the majority of your body by mass. The heavier elements, the carbon that forms the backbone of your DNA, the oxygen that your hemoglobin carries to your cells, the iron at the center of each hemoglobin molecule, the calcium in your bones, all of these were built in the cores of stars that lived and died before our solar system was born. When you breathe, you are processing material that was once inside a star. When you move your hand, you are moving atoms that have existed in one form or another since the universe began. The cosmos is not out there, separate from us, a stage upon which we are merely incidental performers. The cosmos is in us, as surely as we are in it. And this is perhaps the most profound context in which to consider the question of how far we could travel. When we imagine a spacecraft pointing toward a distant star, we imagine a separation. Here, the familiar Earth; there, the unknown beyond. But this separation is, in some sense, illusory. The material of which the spacecraft is made, and of which its crew is made, was forged in the same stellar processes that forged the material of the destination. The laws of physics that will govern the spacecraft's journey are the same laws that govern the nuclear reactions in the target star and the chemistry of any planets that might orbit it. We are not truly alien to the cosmos we imagine exploring. We are part of it. We are the universe exploring itself, as numerous thinkers have pointed out, a claim that sounds almost mystical but is, at its core, simply a statement about the continuity between us and the physical world that produced us. Yet continuity does not imply ease. The fact that we are made of the same stuff as the stars does not make it easier to reach them. The distances remain what they are. The speed of light remains what it is. The energy requirements for interstellar travel remain formidable. And so, if we are serious about the dream of eventually reaching other star systems, if we regard this as a long-term goal for our civilization rather than merely a thought experiment, we must be equally serious about the path to get there. Not the path in the sense of a route through space, but the path in the sense of the technological, social, and philosophical development that would be required. The technological path begins, as it always has, with small steps. The immediate future of human space exploration is almost certainly confined to our own solar system, to the Moon, to Mars, to the asteroid belt, perhaps eventually to the outer planets and their moons. This is not a small thing. Our solar system is itself a place of astonishing variety and richness. The Moon, with its frozen water deposits in permanently shattered craters near its poles, may eventually support human settlements that could serve as stepping stones for deeper missions. Mars, with its ancient river valleys and polar ice caps and evidence of past liquid water, may harbor the most important question in planetary science: whether life has ever existed, or currently exists, somewhere other than Earth. Jupiter's moon Europa, with its global ocean of liquid water beneath a shell of ice, heated by tidal forces from Jupiter's immense gravity, is one of the most tantalizing targets in astrobiology. Saturn's moon Enceladus, which erupts plumes of water vapor and organic molecules from its south polar region, offers something even more accessible than Europa: the ability to sample its subsurface ocean without even landing, simply by flying through the plumes. Titan, with its thick nitrogen atmosphere, and its lakes and rivers and seas of liquid methane and ethane, is an alien world so rich and so strange that a human standing on its surface would feel simultaneously at home. There are clouds, there is weather, there are flowing liquids and erosional landscapes, and utterly elsewhere. These worlds are, by the standards of interstellar travel, absurdly close. Even at the speeds of our fastest current spacecraft, all of them are reachable within years to a decade or two. The exploration and eventual settlement of our solar system is not a distant dream. It is something we are beginning to do. And in doing it, we will develop the experience, the infrastructure, the industrial capacity, and the technology that are the necessary precursors to anything more ambitious. Every step outward in our solar system is a rehearsal for the longer journey. The long journey will require, above all, energy. Not just the energy to propel a spacecraft to interstellar velocities, but the energy to sustain a civilization capable of sustaining the long-term project of space exploration. And energy, in the long run, is available in abundance. The sun alone pours out far more energy in a single second than humanity has consumed in all of recorded history. The challenge is not the supply, but the collection and utilization. A civilization that learns to harvest stellar energy efficiently, through solar collectors in space, through fusion power that replicates on Earth, and in space the reactions that power the sun, through whatever advanced technologies physics permits, would have access to energy resources on a scale that makes the project of interstellar travel look, if not easy, at least tractable over sufficiently long timescales. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, classifies civilizations by their energy consumption. A Type 1 civilization harnesses all the energy available on its home planet. A Type 2 civilization harnesses all the energy output of its star. A Type 3 civilization harnesses all the energy of its entire galaxy. We are currently a Type 0 civilization by this scale. We consume only a fraction of the energy incident on Earth's surface. But the progression from Type 0 to Type 1 to Type 2, while demanding an enormous increase in technological capability, involves no violation of any physical law. It is a path that physics permits, and it is a path that would place all the resources needed for interstellar travel within reach. Consider what a Type 2 civilization, one that has learned to harness the full energy output of its star, could accomplish. The Sun puts out approximately 3.8 times 10 to the power of 26 watts. A civilization with access to even a small fraction of that energy could power matter-antimatter rockets capable of reaching relativistic velocities. It could construct a laser array of sufficient power to push laser-sail spacecraft to significant fractions of light speed. It could build von Neumann probes in the millions. It could, if it chose, begin the slow and patient work of spreading through the galaxy, one star system at a time, carrying with it whatever it had learned and whatever it hoped to find. The question is not whether such a civilization could do these things. It is whether any civilization would want to, and whether any civilization can survive long enough to develop the technology required. Survival is perhaps the most fundamental challenge of all. Civilizations are fragile things. We know of only one, and it has come extraordinarily close to self-destruction multiple times in its brief history, through war and plague and the slow poisoning of its own environment. The technologies that enable exploration, advanced energy systems, powerful computing, biotechnology, are the same technologies that enable destruction if misused or mismanaged. The history of our own species is a testament to the difficulty of managing increasing technological power without the corresponding development of wisdom and cooperation. Whether we will successfully navigate the transition to a civilization capable of interstellar travel, or whether we will destroy ourselves or permanently limit our development long before we reach that point, is the most urgent and consequential question we face as a species. It is a question that no telescope can answer, no particle accelerator can resolve, no mathematical theorem can prove. It is a question that only the long and uncertain experiment of civilization can ultimately settle. But let us remain optimistic for a moment, not from naivety, but from the recognition that optimism, when grounded in evidence and balanced by realism, is a more useful disposition than pessimism for making progress on difficult problems. The evidence for cautious optimism includes the fact that we have not, yet, destroyed ourselves. We have faced existential risks and navigated through them, imperfectly and at great cost, but through them nonetheless. We have built institutions, however flawed, that embody the insight that cooperation across cultural and national boundaries produces outcomes that competition alone cannot. We have developed a scientific tradition that, at its best, is self-correcting and cumulative, a tradition that builds knowledge generation by generation, each adding to what came before, so that what any individual scientist knows today vastly exceeds what any prior human being could have known. And we have, at rare and remarkable moments, demonstrated a capacity for the kind of collective vision and collective will that transforms the impossible into the merely difficult. The Apollo program is perhaps the most vivid recent example. A civilization that had achieved powered flight only 66 years earlier, 66 years, which is within a single human lifetime, set foot on the surface of another world. The engineering challenges were formidable. The political will required to sustain the program was equally formidable. And yet, it happened. 12 human beings walked on the moon. We brought samples of lunar rock back to Earth, conducted scientific experiments in the lunar vacuum, and returned home safely. And then we stopped going, not because we could not, but because the political will evaporated once the competitive impulse that had driven the program, the Cold War imperative to demonstrate technological superiority, was no longer sufficient motivation. This tells us something important, and it is not a discouraging thing. It tells us that when human civilizations find sufficient motivation, they can accomplish things that would have seemed miraculous to previous generations. The challenge for interstellar travel is finding motivation sufficient to sustain the effort over the timescales required, which are not merely decades, but centuries or millennia, far longer than any individual political program can run on inspiration alone. Perhaps the motivation will come from a discovery. Imagine, and this is not science fiction, because it is a possibility that the evidence of exoplanet astronomy is making increasingly concrete. Imagine that we detect, around a nearby star, a planet with an atmosphere whose composition is inconsistent with purely chemical processes, an atmosphere that contains oxygen and methane in concentrations that would rapidly react with each other unless continuously replenished by biological activity. Imagine that we detect, in that atmospheric signal, the chemical fingerprints of photosynthesis, of respiration, of the kind of biosphere that Earth itself would appear to host if viewed from a distant star. Imagine that we have reason to believe that life, not intelligent life, perhaps, but life of some kind, bacteria in an ancient ocean or forests on a sunlit continent, exists on a world 4 or 10 or 20 light years away. What would that discovery do to human civilization? What would it do to our sense of purpose, our sense of what matters, our willingness to invest in the long and costly project of going there to see? We do not know, because it has never happened. But the history of exploration suggests that the discovery of inhabited worlds, even worlds inhabited only by microbes, even worlds that are far and difficult to reach, would transform the project of space exploration from a scientific and technological enterprise into something with a different kind of weight. It would be the discovery that we are not alone in the universe, and that discovery would change everything about our relationship to the cosmos, and to the question of what we should do with the time and the technology we have been given. It would be, arguably, the most important discovery in the history of science. And the James Webb Space Telescope, and the next generation of even more powerful telescopes being planned, may be in a position to make that discovery, or something close to it, within our lifetimes. The possibility of life elsewhere in the universe is, to say the least, not far-fetched. The universe is approximately 13.8 billion years old. Earth formed about 4.5 billion years ago, and life appeared on Earth within a few 100 million years of the planet's formation, suggesting either that life arises readily under the right conditions, or that we got very lucky, or both. The universe had been producing stars and planets for over 9 billion years before Earth formed. In that time, 9 billion years, many stars have lived complete lives, formed planetary systems, had those planetary systems exist for billions of years under relatively stable conditions, and then aged and died. If the conditions for life are not unique to Earth, if chemistry under the right circumstances tends to produce self-replicating systems, then the 9 billion years before Earth formed would have been more than sufficient for life to arise in many places. And some of those places may have had 9 billion years more than we have to develop. 9 billion years is almost incomprehensibly long. It is long enough, in principle, for a technological civilization to have arisen, developed spaceflight, spread to its galaxy, and either still be flourishing or long since gone, and long enough for the evidence of its existence to have faded or been distributed so thoroughly that we would not easily recognize it. The thought of civilizations that have had 9 billion years to develop, 9 billion years to accumulate knowledge, to solve problems, to change and grow and perhaps transcend the limitations that currently constrain us, is one of the most mind-expanding thoughts available to a human being. What would a civilization 9 billion years old know? What would it have become? Would it be recognizable to us as a civilization at all? Would we recognize its artifacts as artifacts, or would they seem to us like natural phenomena, as inscrutable and taken for granted as mountains and rivers? These are not questions with answers, at least not answers we currently possess. They are questions that illuminate the depth of our own ignorance about the space of possible minds and possible civilizations. They remind us that we are very young, and that youth, while it has many advantages, also carries a tendency to assume that one's current perspective is the correct and permanent one. There is a version of the story of cosmic travel that ends in triumph, a version in which humanity, or its successors, solves the energy problem, and the propulsion problem, and the biological problem and spreads, over millions of years, through the local group of galaxies, becoming one of those civilizations that has had time enough to understand things we cannot currently imagine. There is another version that ends in extinction, an early truncation of our story by our own actions, or by some cosmic accident, a supernova too close, an asteroid with our name on it, a pandemic that crosses some threshold our medicine cannot contain. And there are many versions in between. Civilizations that flourish and then contract, that expand and then choose to consolidate, that explore and then decide that the richness of the inner life surpasses the richness of the outer. We do not know which version we are living in. We are too close to the beginning of the story to see its arc. What we can do, what each of us can do, in whatever circumstances we find ourselves, is to remain curious, to look up, to keep asking the questions that have no comfortable answers, the questions that stretch the mind past what it thought were its limits, and reveal that those limits were not walls, but horizons, and horizons, by their nature, recede as you approach them. Every answer we find generates new questions. Every distance we cross reveals new distances beyond. The universe is not a problem to be solved but a depth to be inhabited, and the inhabiting is what we are here for, in whatever time we have. The photons that fell on your ancestors, the same light that illuminated the paintings in the cave at Lascaux, that shone on the first city walls of Sumer, that lit the faces of the astronomers who first mapped the planets, and the mathematicians who first understood why they moved the way they did, those photons came from the same sun that shines on you. And the light you see tonight, falling from stars, some of which may be surrounded by worlds where something is also looking up, that light has crossed distances that take the mind to its edges and asks it to keep going anyway. The universe does not promise us safety. It does not promise us success. It does not even promise us companionship, though it may provide it. What it offers instead is something more austere and more enduring, the invitation to understand. The invitation to look clearly at what is actually there, not at what we wish were there, not at what fear or comfort or habit might suggest, but at what the evidence, patiently gathered and carefully interpreted, actually shows. What it shows is a cosmos of extraordinary age and extraordinary scale, governed by laws that are the same everywhere, filled with matter and energy in configurations of stunning complexity, haunted by the possibility of life in 100 billion corners of 100 billion galaxies, expanding without pause toward a future that it is partly within our power to shape. It is a cosmos that began in a state of almost perfect uniformity and has, through the action of gravity and nuclear physics and chemistry and time, generated the astonishing variety of structures we see today, from the filaments and voids of the cosmic web to the spiraling magnificence of galaxies, to the nuclear furnaces of stars, to the orbiting worlds that circle them, to the thin and improbable layer of life on at least one of those worlds that has, against all expectation, begun to understand the physics of what produced it. We are the universe's way of knowing itself. This is not a mystical claim. It is a description of the causal chain. The Big Bang produced the laws of physics and the initial conditions. The laws of physics produced stars. Stars produced elements. Elements produced planets. Planets produced chemistry. Chemistry produced life. Life produced minds. Minds produce the questions we are asking now. It is a chain of causation that stretches 13.8 billion years, from the first fraction of the first second of the universe's existence to this moment, in which a mind shaped by that entire history is contemplating the history that shaped it. The loop has closed. The universe has become aware of itself, at least in this small corner, through us. How far could we travel before the universe stops us? Before the expanding cosmos carries the last unreachable galaxy beyond the last possible horizon, before the last star dies, and the universe achieves its final dark equilibrium, we have, at minimum, tens of billions of years and hundreds of billions of galaxies worth of possibility ahead of us. Whether we will use it, whether we will survive our own adolescence long enough to grow into the vast and patient explorers that the cosmos seems, in its patient abundance, to have been waiting for, that is not a question the universe can answer. It is a question that we answer every day with our choices and our courage and our willingness to keep looking up. The field is still there. The night is still clear. The Milky Way arches overhead in its immense and silent river of light, and somewhere in that river, lost among 200 billion stars, a single yellow star shines with a warmth that made our oceans move, and our chemistry breathe, and our minds begin their long and still continuing journey toward understanding. That star, our star, the only one we have ever known, the one that knows nothing of our adoration and goes on burning regardless, is one of 200 billion in this galaxy alone. And this galaxy is one of 2 trillion in the observable universe. And the observable universe is perhaps one of an enormous, possibly infinite, ensemble of universes, though that idea remains at the edge of what physics can currently say anything rigorous about. Within all of that, within the staggering and almost incomprehensible vastness of what exists, we are small. We are brief. We are local. We are dependent on conditions so specific that the probability of their occurring by chance seems vanishingly small, though chance is precisely what produced them, given enough time and enough space in which to act. We are temporary arrangements of atoms that will eventually be dispersed and incorporated into other arrangements, into the soil, into other organisms, ultimately into the interstellar medium from which new stars and new worlds will someday form. We are not permanent. We are not central. We are not, as far as we can tell, the purpose toward which the cosmos has been aiming. But we are here, right now, at this particular moment in the long arc of cosmic history, when the universe is still young enough to be full of stars, when the galaxies are still close enough to each other to be reachable in principle, when the physical laws are still favorable to the complexity and the chemistry and the warmth that life requires. We are here at a moment when it is still possible, not easy, not guaranteed, but possible, to look up and imagine going there. That possibility is a gift, even if no one gave it intentionally. That possibility is the universe's most extraordinary feature, stranger than any black hole, more profound than any supernova, more worth protecting than any treasure a civilization could accumulate. The grass bends in a wind that is nowhere in particular to go. Overhead, light that left its source before our civilization began falls on a face that has been shaped by 4 billion years of life adapting to this particular world. And in those eyes there is something that should not be there, not by any simple calculation of evolutionary advantage, something that goes beyond the needs of survival and reproduction, something that reaches past the immediate and the practical toward the distant and the abstract, something that looks at the stars and feels not indifference but wonder, not resignation but aspiration, not the constriction of limits but the exhilaration of a horizon that will always lie just a little bit beyond where we have reached so far. That is what we are. That is what we have always been, since the first human mind was complicated enough to notice the sky and ask what it was. We are the asking. And the universe, in its magnificence, is the answer that we are always, endlessly, in the beautiful and necessary process of finding. Go gently now. The stars will still be there when you wake. And yet, before we rest, there is one more thread worth following, one more layer of the question worth unfolding in the quiet way that night thoughts tend to unfold, slowly and without urgency, like a tide coming in across a wide and gentle shore. Because we have spoken of the limits that physics imposes, the speed of light, the energy requirements, the cosmological event horizon, and we have spoken of the limits that biology imposes, radiation, microgravity, the fragility and brevity of human life, and we have spoken of the limits that civilization imposes, the difficulty of sustaining projects across centuries, the fragility of political will, the ever-present risk that we might not survive our own technological adolescence. But there is one more limit, and it is perhaps the strangest of all, and it is this, the limit of knowing where to go. The universe, as we have seen, is very large. The observable universe contains 2 trillion galaxies. Even confining our ambitions to our own Milky Way, there are between 200 billion and 400 billion stars, each of which might harbor planetary systems, each of whose planetary systems might contain habitable worlds. The number of possible destinations is, for any practical purpose, infinite. And yet, not all destinations are equally interesting. Not all stars are equally suitable as the anchors of inhabited worlds. Not all planetary systems offer the same promise of richness and complexity. And so any civilization contemplating interstellar expansion faces, before the engineering challenges and the energy requirements, a prior challenge, deciding where to go. This is, in its way, a beautiful problem. It is the problem of choosing from abundance, of navigating not scarcity, but an almost embarrassing richness of possibility. And the tools we use to address it are the tools of astronomy and astrophysics, the careful, painstaking observation of star systems from a distance, the interpretation of the spectral signatures of stellar atmospheres, the detection of planetary transits, the measurement of radial velocities, the eventual analysis of planetary atmospheric compositions. These tools, already powerful by historical standards, are developing with remarkable speed. The next generation of space telescopes and ground-based observatories will be capable of directly imaging Earth-like planets around nearby stars and analyzing their atmospheres for signs of biological activity. Within decades, we may have a short list, not a definitive answer, but a credible set of candidates, of star systems that appear to harbor worlds where something interesting is happening in terms of chemistry and perhaps biology. That short list, when it exists, will be one of the most consequential documents in human history. It will be the first empirically grounded answer to the question of where, out there, we might find something worth the journey. It will be the product of thousands of years of astronomical observation, centuries of telescope building, decades of space astronomy, and the cumulative scientific and engineering effort of hundreds of thousands of human beings. And it will point, with whatever accuracy our instruments can achieve, toward lights in the sky that are not merely points of navigation or objects of wonder, but places where something might be alive, where something might be happening, where the great experiment of chemistry and complexity that began on Earth 3.8 billion years ago might have been running in parallel, in ignorance of our existence, for its own incomprehensible span of time. Imagine receiving that list. Imagine opening it, metaphorically of course, since by the time such a list exists, the concept of opening a document might be as quaint as we now find the concept of unrolling a scroll and reading, for the first time, the names or designations of star systems that have been identified as potentially harboring biospheres. Imagine knowing that within 4 light years, or 10, or 20, there's a world where the sun rises every morning over an ocean that is not dried in 1 billion years, where the chemistry of life has had time enough to produce complexity that we cannot yet imagine. What would you feel? What would any of us feel? I think the answer is something that combines the exhilaration of discovery with a kind of vertigo, the vertigo of a horizon that suddenly, abruptly reveals itself as closer than you thought. The vertigo of realizing that the question is no longer purely academic, that the answer matters in a way that requires a response. The response, of course, will not be immediate. Even if we identified tomorrow a planet 20 light years away with unmistakable biosignature gases in its atmosphere, the journey to reach it is still decades or centuries away with any technology we can currently envision. But the discovery would change the psychology of the project. It would shift the question from whether we should try to reach other worlds to which world we should try to reach first. It would transform the dream of interstellar travel from a vague aspiration into a mission with a specific destination and a specific purpose. And missions with specific destinations and specific purposes, as the history of exploration demonstrates, have a way of mobilizing the kind of sustained collective effort that more abstract aspirations rarely manage to sustain. There is something in us. Perhaps it is the legacy of 4 billion years of life always trying to fill the next available niche, always pushing into the next unexplored territory, always turning the corner to see what is around it, that responds to the knowledge of a specific destination. The ocean beyond the horizon was once a limit. It became a destination when someone built the first seaworthy vessel and pointed it toward the unknown. The moon was once the ceiling of human experience, the bright disk in the night sky that pulled the tides and inspired the first mythologies. It became a destination when we understood what it was and built the engines to reach it. The nearest star system with a potentially inhabited world will, I suspect, make the same transformation, from a light in the sky to a destination, the moment we have genuine reason to believe that something is living there. This is the deepest form of the answer to the question of how far we could travel. The physical limit is the cosmological event horizon, roughly 16 billion light-years away. The practical limit, with any technology we can currently envision, is a few dozen light-years, reachable in centuries by crewed spacecraft or decades by robotic probes. The motivational limit, the distance beyond which we would not be compelled to try, may be much shorter than the physical limit, but is not determined by physics at all. It is determined by what we find. If the nearest inhabited world is 4 light-years away, we will have reason to try for it within a few generations. If the nearest inhabited world is 10,000 light-years away, the calculus changes significantly. If we are alone in the galaxy, if life is so rare that no other world in the Milky Way has ever produced it, then the motivational landscape of interstellar exploration changes completely, and the question becomes not whether to seek out life, but whether to bring it, to be the first wave of a biological expansion that would transform a galaxy currently lifeless except in one small corner. Each of these possibilities is genuine. Each deserves to be taken seriously. And the difference between them, the difference between a galaxy rich in life and a galaxy empty of everything but us, is a difference that will be among the most consequential facts ever established about reality when it is established. We are right now in the peculiar position of not knowing which universe we inhabit. We know that life arose on Earth. We do not know whether that event was common or vanishing or rare. We know that Earth is not particularly special in any obvious physical sense. It orbits a common type of star at a distance that allows liquid water on its surface, and there are billions of similar configurations throughout the galaxy. But commonness of conditions does not guarantee commonness of outcomes. Life may arise readily on any world with liquid water and the right chemistry. Or the step from chemistry to biology may be so improbable that it has happened in the observable universe only once. We do not know. The answer is out there, written in the spectra of planetary atmospheres, and the signals of radio telescopes, and the eventual observations of spacecraft that may one day pass through the atmosphere of another world and analyze its air. Finding that answer is, arguably, the most important scientific project our civilization has ever undertaken. In the meantime, in this interim period between not knowing and knowing, between dreaming and doing, we have the night sky. We have the photons that fall without discrimination on anyone who takes the trouble to go somewhere dark and look up. We have the capacity for wonder, which is not merely a pleasant feeling but a cognitive state that predisposes us to learning and discovery, the state in which the mind is open, attentive, and willing to be surprised. We have the questions themselves, which are worth more than they cost, worth more than the comfort that certainty might provide if we simply stopped asking and decided that we know enough. How far could we travel before the universe stops us? Far enough to reach the nearest stars, if we build the right engines. Far enough to cross the galaxy, if we have enough patience and enough time. Far enough to reach the nearest galaxy cluster, if we have the ambition and the centuries. Far enough, perhaps, to colonize the entire reachable universe, the hundreds of billions of galaxies within our cosmological event horizon, if we are lucky enough to survive and wise enough to use our survival well. And not far enough to reach what lies beyond the event horizon, the galaxies already receding beyond all possible contact, the regions of the universe that are already, and permanently, and forever beyond us. That limit is real. That limit is absolute. That limit is the universe telling us, with perfect consistency and perfect indifference, that it is larger than we are, that not everything is ours to know, that there are doors that cannot be opened and distances that cannot be crossed. This is not a tragedy. Or rather, it is a tragedy in the same way that mortality is a tragedy, real and not to be minimized, but not the whole story. The whole story includes everything that can be done before the limit is reached, and everything that can be understood before the light goes out, and everything that can be felt and created and shared in the space between the beginning and the end. The whole story is what we are living, right now, in this brief and remarkable and irreplaceable moment in the history of a cosmos that mostly does not know it exists, and mostly does not care, and mostly will not notice when we are gone. But we know. We are here. We notice. We care. And in the noticing and the caring, in the act of turning a wondering face toward an ancient and indifferent sky, something happens that the laws of physics do not predict and cannot fully describe. Something that might be the most extraordinary thing in the universe, if only because it is so rare and so fragile and so insistent on continuing despite all the odds against it. Something we call, for lack of a better word, consciousness. The universe, knowing itself through us, asking itself the only question that really matters: how far is there to go? The answer, always, is further. And the journey, always, has already begun. Rest now. Let the darkness be a kindness. The stars will hold their positions through the night, burning with the same patient fire that has been burning since before the first living thing drew its first breath on this or any world, and they will still be there in the morning, a little further away than they were yesterday, because the universe is still expanding and has never once considered stopping. And we will still be here, small and brief and full of questions, still looking up, still wondering, still reaching for something just beyond our grasp, the way living things have always reached, the way the universe seems, in its most extraordinary accident, to have been waiting for something to do. Sleep now. The cosmos is immense, and the immensity is patient, and there is time, not infinite time, but enough time, for everything that matters. Close your eyes. Let the light of distant stars fall on you in the dark. You are made of that light. You always have been. But let us linger just a little while longer. There is one more quality of the night sky that deserves our attention before we release the thread of this contemplation and let it drift back into silence. It is something that takes a while to notice, something that requires a certain kind of looking, not the focused, effortful looking of someone trying to identify a specific star or constellation, but the soft, peripheral looking of someone who is relaxed entirely into the experience of simply being under the sky. When you look at the sky this way, you begin to notice that it has texture. Not the texture of a surface, but the texture of depth. The stars are not all at the same distance. They are not a flat ceiling painted with lights. They are points scattered to a volume that extends, in some directions, for billions of light years, and the ones you see closest to you and the ones you see farthest from you are separated not by a few feet, but by thousands of light years. The sky has depth the way a forest has depth, the way the ocean has depth, and when you truly feel this depth, when you stop seeing the sky as a background and start seeing it as a volume, the experience of looking out changes completely. You are not looking at something. You are looking into something. You are looking through layers of time and space into a volume so vast that your own existence within it is all but imperceptible by any scale you can apply. And yet you perceive it. And that perception, that particular, peculiar experience of a small and temporary creature recognizing that it exists within something unimaginably larger than itself, is one of the most specifically human things there is. It is not clear that any other species on Earth experiences the night sky in quite this way. Other animals navigate by it. Birds read it for migration routes. Sea turtles orient by it on moonlit beaches. Bees and other insects use the polarization of sunlight, filtered through the blue sky, as a compass. The sky is a tool, for most of the living things on this planet, in the way that a hammer is a tool, useful used, but not contemplated. Only we, as far as we know, look at the sky and ask not just where it leads, but what it means. Only we are troubled and exhilarated simultaneously by its immensity. Only we have built temples and cathedrals and observatories in its honor. Only we have dedicated entire lifetimes to understanding it, to mapping it, to decoding the messages written in its light. This peculiarity of ours is worth noticing. It is worth treating as a clue. A clue about what? About ourselves, primarily. About what kind of creature we are, and what kind of future we might be capable of building. A species that looks at the cosmos and feels the tug of the beyond, that builds telescopes and rockets and mathematical frameworks to understand what it sees, that writes poetry about the stars and sends spacecraft toward them. Such a species is not finished. Such a species is, in the most literal sense, at the beginning of something. We have been doing science for roughly 400 years. We have been doing spaceflight for less than 100. We have been writing things down for about 6,000 years, and organized civilizations for perhaps 10,000. On the timescale of the universe, on the timescale even of our own solar system, which has been here for 4.5 billion years, we are brand new. We are barely a footnote, a blip, a momentary stirring in the history of a cosmos that has been producing stars and planets, and perhaps life, for almost 14 billion years. Brand new things are not yet finished. Brand new things have most of their stories still ahead of them. And whatever that story will be, whether it unfolds over centuries or millennia or the billions of years that remain before the sun exhausts its fuel and the earth is absorbed into a red giant, it begins right here, in this moment, with the particular quality of attention that a wandering mind brings to an ancient and inexhaustible sky. There is a concept in astronomy called the cosmic perspective, and it is one of the most powerful things that science has ever offered humanity. The cosmic perspective is what you get when you step back, in your imagination, in your understanding, in your felt sense of where you are and what you are, far enough to see the whole picture, or as much of the whole picture as is currently visible. It is the perspective from which Earth is a mote of dust suspended in a sunbeam, as Sagan so memorably put it. It is the perspective from which the entire span of human history, from the first stone tools to the most recent news, is a single thin slice of a cosmic story that began 13.8 billion years ago and will continue for trillions of years more. It is the perspective from which wars and borders and the petty cruelties that humans visit on one another look not just wrong but absurd, a waste of the extraordinary rarity of consciousness, a squandering of the cosmic accident that produced creatures capable of understanding the universe they inhabit. But the cosmic perspective is not only humbling. It is also, paradoxically, empowering. It is empowering because it reveals the true scale of possibility. It reveals that the constraints we accept in our daily lives, the borders, the categories, the hierarchies, the assumed limits of what is achievable, are not natural features of reality. They are human constructions, temporary arrangements that we have made and can unmake. The universe does not require that we treat each other with contempt. The universe does not require that we organize our civilizations around the accumulation of power by the few at the expense of the many. The universe does not require that we exhaust our planet's resources and a few centuries of industrial expansion and leave nothing for the generations that will follow. These are choices we have made, and choices that are made can be unmade, or made differently, if we can find the will and the vision to do it. The cosmic perspective tells us that we have, in principle, billions of years ahead of us. What we do with those billions of years, if we are careful and fortunate enough to survive into them, is genuinely open. The universe has not written our ending. The universe, for all its indifference, has given us the extraordinary gift of a story that is still being written by us. The last star in the observable universe will not go dark for trillions of years. The red dwarf stars, the smallest, dimmest, most numerous type of star, burning their hydrogen fuel so slowly that they last 100 times as long as the sun, will still be glowing faint and red when the universe is 100 trillion years old, roughly 10,000 times its current age. In those far future eons, if anything survives, if any form of intelligence persists, whether biological or digital or something we cannot currently imagine, the night sky will look nothing like ours. The sun will be long dead. The Milky Way will have merged with Andromeda and become a single large elliptical galaxy, its spiral arms long since dispersed. The other galaxies will have receded beyond all possible observation, carrying with them whatever life or intelligence they may have harbored, beyond the reach of any signal or any vessel. The night sky will be dark and sparse, populated only by the remaining red dwarfs, and the cooling remnants of dead stars, a sky that looks nothing like the sky above us tonight. And yet, if anything is there to see it, if consciousness has found a way to persist through the long cooling of the cosmos, it will still be the same universe. The same physical laws, the same space-time, the same constants of nature that determine everything from the mass of an electron to the expansion rate of the cosmos. The same universe that produced us, still going, in its patient and inexorable way, toward whatever it is going toward. We do not know what the universe is for, if anything. We do not know whether the emergence of consciousness within it is a central feature or a trivial accident. We do not know whether there is any meaning in the fact that the cosmos has produced, after 13.8 billion years of expansion and star formation and planetary chemistry and biological evolution, creatures capable of asking what it all means. We do not know, and the not knowing is not a failure. It is the condition of being alive in a universe that is larger than any mind it has produced. What we know, what we can say with the full weight of everything we have learned, everything we have observed, everything we have measured and modeled and tested and revised, is that the universe is real, that it follows laws, that those laws permit complexity and life and intelligence, that within the reachable volume of the cosmos there are destinations waiting for the first visitors that will ever approach them, that the window of cosmic accessibility is open, for now, and will close slowly over billions of years, and that we are awake, right now, in what may be a singularly favorable moment in the history of the cosmos to ask the question and begin the journey. We know that the distances are vast and the obstacles are real, and the limits are absolute at their limits, but generous within them. We know that we have barely begun, that everything we have done so far, every telescope, every spacecraft, every equation, every poem written to the stars, is the first hesitant paragraph of a story that has the potential to go on for longer than we can currently imagine. And we know, or at least we suspect, in that quiet and particular way that wonder generates conviction, that this story is worth continuing, that the effort of understanding is worth making, that the dream of the stars, however long it takes to realize, however difficult the path, however uncertain the outcome, is worth dreaming. Not because we are sure of success, not because the universe guarantees a happy ending, but because the dreaming itself, the aspiring, the reaching, the refusal to accept the horizon as a permanent boundary, is part of what we are. It is the oldest part. It is the part that looked up, long before it understood what it was looking at, and felt something it could not yet name, but knew was important. It is the part that has been looking up ever since. The universe will eventually stop us. Entropy will win, as entropy always wins, given sufficient time. The expansion will accelerate, and the galaxies will recede, and the stars will die, and the void will deepen, and the temperature will fall toward absolute zero, and the last traces of structure will dissolve into a darkness so complete and so vital that no word we have is adequate for it. This will happen. It is written in the physics, and the physics does not negotiate. But it will happen at a distance, a temporal distance, so vast that the number of years involved is larger than the number of atoms in the observable universe. Between now and then, there is more than enough space for a story of extraordinary depth and richness and meaning. There is enough space for us, and for whatever we become, to explore and understand and cherish a cosmos that does not need our cherishing but somehow, improbably, wonderfully, has produced creatures capable of offering it. Go then. When the morning comes, go out and look at the sky. Look at it with the knowledge of what it is, not a ceiling but a depth, not a background but a volume, not a decoration but a record, a history, a landscape of extraordinary complexity and age and possibility. Look at the nearest star and know that it is a sun, and that around it may be worlds, and that those worlds may not be empty. Look at the smudge of the Andromeda galaxy, and know that it is 2.5 million light-years away, and contains 1 trillion stars, and that the light reaching your eye right now left it before our own ancestors had developed language. Look at the entire sweep of the Milky Way, and know that you are inside it, that you are a citizen of it, that its 200 billion stars are as much your birthright as the ground beneath your feet. And ask the question again. Not because you expect a final answer. There are no final answers in a universe still busily making itself, but because the asking is the thing. Because the question, properly held, opens something in the mind that nothing else opens quite the same way. Because how far we could travel before the universe stops us is ultimately a question not just about physics, but about us, about what we want, and what we dare, and what we are willing to become in the service of understanding the extraordinary thing we find ourselves inhabiting. The answer is always just a little further than we have gone. And the journey is always, always worth making. Breathe out. Let the night hold you. The stars are burning. The universe is expanding. Everything is exactly as it is, which is to say, more wonderful than it is possible to say. Sleep well.